Hello everybody. In this video we'll be covering one of the sections in chapter 7 of our textbook entitled Chemical Reactions. In this video we're going to talk about chemical equations. So what is a chemical equation? It's a shorthand way of describing a reaction. It provides information about the reaction. It gives you the formulas of both the reactants and the products. It tells you about the states of the reactants and products, meaning like solid, liquid, gas, etc. It gives you relative numbers of the reactants and products that are required for the reaction to take place. And it can be used to determine the masses of the reactants used and the products that can be made. So we can start to get a sense of our scale. If I add this much of this and this much of that, how much product am I going to be able to produce? An important thing to keep in mind is that we still have our conservation of mass. So we know that matter cannot be created or destroyed. Therefore, the total mass before and after the reaction cannot change. And the total mass of the reactants will be the same as the total mass of the products. In a chemical reaction, all the atoms present at the beginning are still present at the end. If all the atoms are still there, then the mass will not change, right? So we're not changing the type of atoms we have, and we're going to have the same number of atoms at the beginning and the end. So we're going to discuss now the combustion of methane. So natural gas is mostly methane. And we tend to burn it in the presence of oxygen in the air in order to produce carbon dioxide gas and gaseous water. Just to note once again that every time something burns, it's when it's combining with oxygen gas. So methane gas burns to produce carbon dioxide and gaseous water. This is the chemical reaction that's going to describe that. So we have methane plus oxygen plus carbon yields, that's what this arrow means, or produces carbon dioxide and water. If we were to draw out a little cartoon, this is what this is representing right now. So we have a carbon and 4 hydrogens represented by the CH4, plus 2 oxygens represented by the O2 is going to yield a carbon and 2 oxygens attached to it, plus an oxygen with 2 hydrogens attached to it. Now, the question I want to ask is, what incorrect assumption was made when we wrote this equation? So is there something wrong about this? And you may have already guessed that the problem that we have is that we don't have the same atoms at the beginning that we had at the end. Okay, if we count up over here, we have 1 carbon, 4 hydrogens, 2 oxygens. If we come over here, we still have 1 carbon, but we have 3 oxygens now. Where did that extra oxygen come from? And we only have 2 hydrogens left when we had 4 hydrogen atoms over here. So there's something wrong here. This isn't in balance. And that's because we assumed that all the reactants combine in a 1 molecule to 1 molecule, and that 1 molecule of each product was created. Okay, so we assumed that it was just 1 methane molecule is going to react with 1 oxygen molecule to produce 1 molecule of carbon dioxide and 1 molecule of water. But most reactions rarely work this way. So let's see how we fix that. How do we balance this equation? So to show that the reaction obeys the law of conservation of mass, the equation has to be balanced. And we do that by adjusting the number of molecules so there are equal numbers of atoms of each element on both sides of the arrow. And the way that we indicate that in our reaction is by adding these guys here. So now we've indicated that we're going to mix 1 molecule of methane with 2 molecules of oxygen, and that's going to produce 1 molecule of CO2 and 2 molecules of water. If we check now, we'll see that this does now add up. We have 1 carbon over here, 1 carbon over here, 4 hydrogen over here, 4 hydrogen over here, 4 oxygens, and 4 oxygens. So let's talk about and do a little review of some of the features that we've seen now and the information that's packed into a chemical formula like this, because there's really a lot of information that's given to us in a really condensed form here. So first off, we know that this reaction is now balanced, okay? And that means that there's going to be equal numbers of atoms of each element on the reactant and product sides, all right? To obtain the number of atoms of an element, we're going to multiply the subscript by the coefficient. So mathematically, rather than drawing out our little cartoon, if we want to figure out how many atoms there are here, we're going to assume that there's a 1 coefficient here. And we're going to multiply a assumed 1 subscript here to see that there's 1 times 1, 1 carbon. Similarly, if we wanted to do hydrogen, it would be this 4 subscript times this 1 that's assumed here. 4 times 1 is 4 hydrogen. Over here, we have a 2 subscript and a 2 coefficient. So 2 times 2 means that this whole thing represents 4 oxygen atoms. Okay? In this water example here, you would have 2 times 2, 4 hydrogens, and 2 times an assumed 1 here, 2 oxygens. A nice way that I like to represent these is to write out each of the different kinds of atoms and then draw arrows on each side, indicating how many you have on the left-hand side of the arrow versus how many you have on the right-hand side of the arrow. And then you go through with each one, adding them all up, and you ultimately get you can ultimately see where you have a loss of balance. Okay? You'll note that sometimes I like to write 2 plus 2 over here. This indicates that this oxygen is in 2 of the molecules. So there's 2 oxygens from the CO2, and there's 2 oxygens from the water. So a little bit of language here. On this side, the left-hand side, we have the methane and the oxygen. And these are what we call the reactants. These are the 2 things that are going to react together. And on the right-hand side, the side that the arrow is pointing to, we have CO2 and H2O. And these are called the products. They're the things that we're going to produce in this reaction. This symbol here, which I'll note is in a parentheses, it's lowercase and it's italicized, this G. Tells us the state of the chemical. And what it's telling us is that these guys are all gases. The number in front of each substance tells us the numbers of those molecules in the reaction, right? So we know that this means that we have 2 oxygen molecules, and we call these coefficients. So we saw that this G here indicates that we were in the gas state, but there's other states that we can be in, and this is how we're going to indicate those. Scripted L is liquid, scripted S is solid, and then this AQ indicates that it's aqueous, which means that it's dissolved in water. We're going to have a section about that later. Sometimes we see energy symbols used above the arrow. This indicates that maybe we had to add heat in order to get the reaction to proceed, for instance. And what we use there is this triangle symbol that is a Greek capital delta. That usually means change, so like a change in energy. But it's also used to indicate heat in chemistry. This thing that looks like an H with a scripted V, this is actually the Greek letter nu, and that indicates that light was added. So sometimes you can get reactions when you add light. We actually see this a lot, like sometimes your dashboard might get discolored, or something you left out in the sun will get discolored and bleached out. That's a chemical reaction that's happening due to the light being there. The word shock is used to indicate a mechanical energy that was added. Maybe if you've ever like seen those fireworks that you throw on the ground and then they pop, that's a chemical reaction that was initiated by a mechanical shock. An elec indicates that electricity was added in order to get the reaction to initiate. So I'm going to go through a procedure for writing a balanced chemical equations. But I do have to put a little caveat on this. This is not the only procedure for balancing a chemical equation. As they get more difficult, it's actually harder and harder to use this procedure. I could go through a pretty elaborate way of balancing chemical reactions using like numerics and stuff like that, but you guys really wouldn't like it. Ultimately, it's easier to do it by what they call inspection, which means that you just kind of look at it and you play around with the numbers a little bit in order to ultimately get it to balance. And the ones that you're given in this class really aren't going to be that difficult to do this with. But using this procedure that I'm going to outline, it's going to kind of give you a useful hand in figuring out how to go about balancing these chemical equations. It's kind of like the thought process you should follow through. I kind of like to think of them like Sudoku. Well, let's jump into it. So first we're going to write a skeletal equation by writing the formula of each reactant and product, okay, without any coefficients. Then we're going to count the number of atoms of each element on each side of the equation. And really, if you want, you can treat the polyatomics as if they are just like one atom, one element, because they're not going to break up during the chemical reaction. They're going to stay the same. Then we're going to pick an element to balance. So we're going to see which ones aren't balanced, and we're going to pick one to balance. If an element is found in only one compound on both sides, we can balance it first. All right. Metals before nonmetals is usually typically the way that you want to go about it, doing it. And you want to leave elements that are free elements somewhere in the equation until the last. So what I mean by that is like where we had our oxygen previously, and that molecule only contained the element oxygen. You want to hold on to that guy to the very end, because it'll be easier to use that to balance in the end. The next thing we want to do is we want to find the least common multiple, the LCM, of the number of atoms on each side once we decide which element we want to balance. If you don't remember what the least common multiple is, it's the smallest number that you can get that has the two values as its factor. So the least common multiple of 3 and 2 is going to be 6. This least common multiple of like 3 and 5 would be 15. It's often the two multiplied together, but not always. We'll multiply each count by a factor to make it equal to the LCM. All right. And then we're going to use this factor as the coefficients in the equation. All right. The LCM that we need to get, the factor we have to multiply to get to that LCM. If there's already a coefficient there, multiply it by the factor. It must go in front of entire molecules, not between atoms within a molecule. So you don't get to change the proportions within the molecule. You only get to have more or fewer whole molecules. So that probably was pretty confusing. Let's look at an example, and I think you guys will start to see how we're going to go about doing this. So let's look at the example when magnesium metal burns in air. It produces a white powdery compound called magnesium oxide. So there really wasn't even a question here, but sometimes they won't actually give you the equation. They'll just say balance, and then they'll give you a statement like this. So this is where we need to start to use our skills to be able to turn names into actual chemical formulas, and to use indicator like Burns to know that that means that we're going to add oxygen. But I try not to do too many gotchas in this class, so I typically am going to give you the equation. So we have this magnesium solid, right? We know that metals are solids. We're going to add oxygen gas, and we're going to produce magnesium oxide. We know the formula for this because we know that magnesium tends to have a +2 charge, and oxygen tends to have a -2 charge. So this is what magnesium oxide is going to look like. Now, if we count the number of atoms on each side, we have 1 magnesium here and 1 magnesium in that molecule. We have 2 oxygens over here as indicated by the subscript, and we have 1 oxygen over here in this guy. So the first thing we want to do after we've done that count is to pick an element to balance. We want to avoid the elements that are in multiple compounds, and we want to do the free elements last. But here it was really easy to pick this out because our magnesium is already balanced. We have 1 here and 1 here, so we kind of have to balance the oxygen first. So next you want to find the LCM of both sides. So let's see if we can indicate what exactly that's going to be for this. So what I'm saying when I say that is basically we have 1, 2, and we have 1. Okay, the least common multiple that I can find between them is going to be 2. I can multiply 1 by 2 to get 2 over here, and I can multiply 1 by 2 to get 2 over there. All right, it's the smallest number that I can multiply these two by in order to multiply some number times these two subscripts in order to get them to be the same. So what we need to now do is use these values as the coefficients here and here, and then recount how many atoms we have on either side. So we're going to use those as the coefficients in front of the compounds containing the element. So here we need to put that 2 that we used as our least common multiple over here, our factor over here to get the least common multiple. Over here we use the 1 that we had over here, but you don't typically write that, so we just didn't have to change that one. And we get this guy. Now we need to recount how many we have on each side. So we have 1 magnesium still. We have 2 times 1 magnesiums here. And we have 1 times 2, so we just have the 2 oxygens there. And we have 2 times 1, 2 oxygens on this side. So now we see that the magnesium is no longer balanced, but we did balance our oxygen. But that's fine, and the reason is because this is a pretty easy one. Magnesium is all by itself over here. So by manipulating the coefficient in front of this guy, I can change the magnesium without affecting the oxygen. And that's what we meant, what I meant when I said that you wanted to save the free ones for last. It's always convenient when you can change one of the coefficients and change one of the atoms without having to affect the others. So if we put our 2 in front of that magnesium, we can see that we'll do a little math here and get 2 times 1 magnesiums on this side. And then if we do our recount, we see that we now have it all balanced out. We have 2 magnesiums here, 2 magnesiums here, 2 oxygens here, and 2 oxygens there. Let's take a look at another example. So under appropriate conditions at 100 or 1000 degrees Celsius, ammonia gas reacts with oxygen gas to produce gaseous nitrogen monoxide and steam. So first thing we need to do is write the skeletal equation. But often when we're given something that's a little trickier like this, it's first easier to just write it out in words. Just take the words directly from the problem and write those out. So we have ammonia plus oxygen, and we got that from ammonia gas reacts with oxygen gas. This arrow literally means to produce gaseous nitrogen monoxide, so nitrogen monoxide is a gas, and steam, which we know is water in the gas form. After that, you can actually just go and look these up if you're not sure of any one of them. And we wind up with this guy right here. So there are a couple of checklist things here. So it's nice to identify the diatomic elements like our oxygen. Identify if you have any polyatomic ions, right? In case any one of these had any polyatomics in it, you could go and look those up so you can remember those structures. And then finally you can determine the formulas, often by doing the ionics or something, or honestly just looking up one that you're not sure of. So the first thing we're going to do is count the number of atoms on each side. We have one nitrogen here, one nitrogen here. We have 3 hydrogen here, and 2 hydrogen in our water. We have 2 oxygens here, and we have 1 oxygen from NO and 1 oxygen from our water. So we have 2 and 2. Oxygen is balanced. Nitrogen is balanced. It's pretty obvious that the first thing we might want to balance here is going to be hydrogen. So it's also nice to remember that we want to avoid elements in multiple compounds on the same side. So oxygen was in NO and water. You don't want to start with that. We're going to find the least common multiple of both sides. And then we're going to multiply each side by a factor so it equals the LCM. So if we wanted to balance the hydrogen here, we had 3 and we had 2. So what you're going to want to do is multiply the 2 times. There's nothing that we can multiply 2 by to get 3. So we want to multiply 2 by 3 to get 6 and 3 by 2 to get 6 over here. So now that we know our factors, we're going to use them as the coefficients in our reaction. Don't forget where you need to actually place those coefficients is in front of the molecule that contained the element we were trying to balance. So we were trying to balance hydrogen, so we put the 2 in front of the molecule that contains hydrogen. We put the 3 in front of the molecule that contains hydrogen. And then we set up our math so that we can do our count again. We now have 2 times 1 nitrogens on that side, 1 nitrogen on this side, 2 times 3 hydrogens, 3 times 2 hydrogens on that side, 2 waters on this side, 3 times 1 oxygen plus the oxygen from this molecule here. This is why sometimes I like to write these as like 1 plus 1 over here, so that I can change just the 1 when I'm doing out my little math. If we go ahead and do that math out, we get our new count. Okay, we have 2 and 1, so this isn't balanced yet. Hydrogen is now balanced, and the oxygen isn't balanced yet either. We have 2 and 4, but we have our ace in the hole, which is going to be this oxygen right here. So in the end, it's going to be pretty easy to balance this oxygen. And there's even a little trick to doing it that I'm going to show you in a second. So the first thing we want to do is we want to balance this nitrogen, because balancing the nitrogen over here is going to throw off our oxygen again. And we want to save this guy for last. So to balance the nitrogen, we have that 2-1 situation. So we want to multiply this guy by 2. And that winds up multiplying this 1 factor here by 2 as well. Once we do that math out, we have the N balanced, we have the H balanced, but we have 5 oxygens over here, 2 oxygens over here. And we still have our little ace in the hole right here of this oxygen. Now, we do have a problem in that there's no simple number that I can multiply 2 by that's going to give me 5. But you don't actually have to let that sway you, okay? What number could I put there that would give me 5? That I could multiply by 2 and give me 5? What I could put there is a fraction. I could put 5 halves. Okay, which I wrote here as 2.5. And if I insert 2.5 in there, well, now I have a factor I'm going to multiply by here that will give me that 5. But I can't just leave that fraction there. Just like when we were working before to do the empirical formula, we don't want to leave that fraction there. But we can multiply all of the coefficients by a number that's going to allow us to clear that value out. So in this case, we have 2.5, and that's a half, right? So just like before, we're going to want to multiply by 2. So if we multiply all of the coefficients by 2, we get our final answer. Okay, 4, 5, 4, and 6. And now, if we do our math out, we'll see that we do in fact have balance. 4 and 4, 12 and 12, 10 and 10. So it's a little confusing to put a fraction in for one of these guys here. And you really don't want to get into a situation where you have multiple fractions for your coefficients. That's going to be difficult to find a factor that's going to work for you. But if you're down to the very end, you've saved that element that has just one type of atom in it, and you need to put a fraction in there to make it all work, it's actually your friend to do that. Go ahead and do it, and then you'll be able to find a value to multiply by that will get you all whole number values. So let's do a little practice now. When aluminum metal reacts with air, it produces a white powdery compound called aluminum oxide. We'll keep in mind that reacting with air means reacting with O2, and we'll write out our write this all out in words. So we have aluminum solid plus oxygen gas is going to produce aluminum oxide. We should be able to get a formula like this. And I'm going to let you guys take a moment and see if you can balance that. Okay. So the correct balance would look like this. And if you guys were following along the procedure, you might have wound up with 3 halves here for the oxygen, and then multiplied them all by 2 in order to get this final answer. Acetic acid reacts with metal aluminum to make aqueous aluminum acetate and gaseous hydrogen. So acids are always aqueous because acid only makes sense inside of water. We learned that previously. Metals are solid except for mercury. We learned about that when we were talking about the periodic table. And acid metal reactions tend to liberate hydrogen gas. Putting all those facts together, we come up with this formula here. Aluminum solid plus acetic acid. I could have just looked that formula up. It's going to yield aluminum acetate plus gaseous hydrogen. I'll mention that this acetate here is one of our polyatomics. So we knew what the charge on that was going to be. We knew it was going to be a -1. And we know that aluminum has a +3 charge. So that's where I'm getting this formula from. I'll give you guys a moment to try and balance it. This one's a little trickier, but if you treat the acetate as just a single atom that's not going to break up during the process, it actually makes it a lot easier. So in the end, we get this balance here, and we can see that it's going to take 6 equivalents of acetic acid, and we're going to produce 3 equivalents of hydrogen. These are probably the two that were a little tricky to balance. Combustion of ethyl alcohol. So this is really a simple phrase that contains a lot of information in it. We know that combustion is burning, and therefore we're going to have a reaction with O2 gas. We know that combustion compounds containing carbon and hydrogen always make CO2 gas and water as products. And we can look up the formula for ethyl alcohol. This is ethanol, the same kind of alcohol that you drink or is in gasoline. So we have ethanol plus oxygen gas is going to yield CO2 and H2O. I'll give you guys a moment to try and balance that. And we get this as our final answer. Again, it would have been very nice if you guys had waited to the end to balance the O2 gas. It tends to make the overall process go a lot easier. We can try one more combustion, the combustion of liquid butane in a lighter. Bute literally means 4. We have C4H10 as a liquid because it's indicated in the problem, plus our O2 gas. This only has carbon and hydrogen. It's going to produce CO2 and water. I'll give you guys a moment to balance it. And we wind up with this balanced equation in the end. And you probably wanted to use a fraction here in order to balance this guy at the very end. Now, I realize that these practice problems weren't particularly helpful because we didn't go through them step by step. But I did want to give you guys a little bit of exposure and let you try it out a little bit for yourself and then have an answer and that you could compare to. If you are struggling with doing these types of balancing problems and stuff, I understand a lot of students do. Reach out to me early on in the week and we can schedule an appointment and we can talk about it together.